Thank you very much to the organizer. No need to say I feel very honored to present a keynote speech at the GEA International Conference online. I'm Wang from School of Soil and Water Conservation, Beijing Forestry University. We all know that interrill erosion occupies an important position in the soil erosion processes. Water movement, including both surface and subsurface sources, is the dominant mechanism in shaping slopes. From the conceptual hill slope model, we can see that different hill slope positions will have different hydrological conditions, and furthermore, the different hydrological conditions will affect erosion processes. For example, drainage conditions are predominant near upper slope area. The small amounts of surface flow from the upper slope area lead to interrill dominant processes. And for the middle and down slope, the increased water from upslope area enhances the concentration of slow surface flow and resulting in rill erosion. Moreover, near the toe of slope, seepage may occur during period of excessive soil moisture. Sediment deposition is another significant process at the bottom position. However, previous studies were usually conducted under a given drainage condition and failed to take account the effect of near-surface hydraulic conditions. Seepage and drainage conditions showed significant effect on erosion processes. Under drainage conditions, the additional section from the downward flow hold down the aggregate in place and increase the resistance of soil detachment. And the erosion pattern is mainly interrill. And due to high soil strength and low soil erodibility, sediment regime is detachment limiting. Seepage flow enhances the quake condition as interparticle force are reduced, and it also reduces the soil strength, resulting in severe rilling on the slope, and the sediment regime is transport limiting. Here are some photos for the seepage-induced erosion. We can see that the severe phenomenon indicates that we cannot ignore the effect of near-surface hydraulic conditions on erosion processes. It's well known that detachment can occur through the expenditure of raindrop and flow energy. Here we provide a schematic of how the various detachment and transport mechanisms are influenced when the shear strength is used as a measure of the inability of flow to detach and transport soil material. In flows without raindrop impact, flows must exceed a critical flow condition, below which no detachment by flow occurs. However, raindrop impacting flows, which is less than about 3 drops diameters, can detach soil particles when the critical flow condition has not been exceeded. In rain-impacted flow, coarse material, particularly sand and soil aggregates, can be moved by raindrop-induced sorting, raindrop-induced rolling, and flow-driven sorting and flow-driven rolling. Before meeting those critical conditions, coarse material can be moved by raindrop-driven sorting and rolling. Whenever detachment occurs, either by the expenditure raindrop or flow energy, fine material moved in complete suspension loads. Although there is a lot of milestone for interrill erosion research, but some scientific questions about the interrill erosion processes remain obscure. When we consider the hydrological conditions of slope, there are some gaps for the detachment, transport, and deposition processes. We're still wondering which is the dominant erosion processes for different hydraulic conditions. Moreover, the dominant transport mode and spatial variations. However, few studies have been conducted with the goal of understanding the impacting of the near-surface hydraulic gradient on the interior erosion processes. Most study is focused on the drainage condition and developed lots of useful and meaningful equations, which is widely accepted and used in erosion prediction models. But this progress is lack of adjustment for near-surface conditions. It's easy to assume that a given rain intensity or runoff results for the same soil loss. So, should we include the near-surface hydraulic condition in the interior erosion processes? I think it's still a big challenge. To solve this problem, we proposed two hypotheses. The first one is thin sheet flow may not have sufficient power to detach soil particles within the underlying surface without raindrop impact. The second hypothesis is that varied near-surface hydraulic gradients promote the dominant erosion process changes. And there is three main objectives for this study. The first one is to reveal the temporal and spatial variation of the interior erosion processes. The second is to identify the dominant erosion processes and transport modes. And the last one is to improve interior erosion predict equations. A clay loam is used in this study. The soil organic matter is 2.1%, clay content is 22%, and silt content is 54%. 6 different powdered RE oxide was used in this study to track sediment movement and deposition in space. The RE oxides were placed in different slope segments and layers. The top 1 cm layer of the interior erosion pan was primarily used to track interior erosion and identify the potential sediment sources. The underlying 1 to 2 cm mixed with TB to identify the occurrence of real erosion. 3 near-surface hydraulic gradients include drainage, saturation, and seepage were designed by adjusting the soil moisture and pressure head. 3 rainfall intensity with rainfall uniformity greater than 90% were selected. A rotary sprinkler simulator system with a rainfall height of 12 meters above the interior erosion pan was used in this study. 2 slopes were used in this study. The background concentration of rare earth elements are listed in the table. The designed application concentration of REE oxide was at least 20 times more than the background. The amount of soil loss from each tracer segment and sediment deposition were calculated based on the mass balance, and the interior erosion rate were calculated based on the cumulative slope length. Now we shift to the results section. Firstly, we should make sure the reliability of RE tracing in interior erosion processes. From the result, we can see that TB traced soil was not detected in the sediment samples. It means that no rills were formed during this study. We also found that the RE tracing error decreased as the rainfall intensity increased, and the near-surface hydraulic gradients shift from the drainage to seepage condition. And the average relative errors is less than 30%, which is considered acceptable. The trend of soil loss from each tracer segment was complex. For the low soil The trend of soil loss from each tracer segment was complex. For the low rainfall intensity with drainage or saturation conditions, there was an obvious increasing trend of soil loss from each tracer segment. However, for higher rainfall intensity and seepage conditions, the interior soil loss from each tracer segment first decreased and then remained stable. The changing trend of temporal variation in the soil erosion process depends on the near-surface hydraulic gradient, the shielding and crushing processes, and the maximum interior soil loss merged downslope as the rainfall intensity and seepage conditions increased. The contribution of interior soil loss from each tracer segment was fairly stable. The contribution from the CE segment was the smallest, ranging from 0.4% to 5%. Due to the limited runoff, the particles pre-detached by raindrop splash could not be transported to the outlet. For the drainage condition, the average contribution first increased and then decreased. But for the seepage condition, it was continuous increase. Here is some information about the spatial variation of interior erosion and sediment deposition. The erosion peaked at the SM segment for the drainage conditions under 30 mm per hour intensity, and the erosion peaked at the GD segment at 60 and 90 mm per hour. Under the drainage conditions, the slopes of the curves diminished gradually as the downslope distance increased. This result implies that the transport-limited processes may have dominated the interior erosion processes for the drainage conditions. For seepage conditions, the slope of the curves increased gradually as the downslope distance increased. This result implies that the detachment-limited processes may have dominated the interior erosion process of the seepage condition. There was a remarkable difference in the sediment deposition rates along the slope. The contribution of sediment deposition above the tracer segment was 7%, which was obviously less than that below the tracer segments. This is because the sediment deposition above the tracer segments was caused by splash transport. It was also found that the sediment deposition rate along the eroding slope was seldom uniform and fluctuated sharply, implying that the soil particles detached by raindrops or raindrop impact sheet flow might be transported as bed load in waves by rolling or creeping. For an equivalent runoff, the interior erosion rate increased from the drainage to seepage condition. Sediment particles were not moved under only exfiltration flow without rainfall impact. It implying that exfiltration flow energy was very small. Hence, we assume that the runoff detachment and transport capacity were likely insufficient due to the lack of raindrop impact. To further explore this hypothesis, we conducted observational experiments of runoff soil with equivalent rainfall intensity and directly determined the critical flow rate. Results showed that the loose soil particles were not detached under the thin sheet flow. It was also observed that the critical flow rate decreased when the near-surface hydraulic gradient shifted from the drainage to seepage conditions, which supports the first hypothesis of this study. The average raindrop-induced detachment rate was higher than interior erosion rates for the drainage conditions, indicating that the dominant interior erosion processes was mainly transport limited. However, the average range of induced detachment rate were lower than that interior erosion rates, when the near-surface hydraulic gradient shifted from the drainage condition to seepage conditions. Thus, it can be inferred that the dominant processes of the interior erosion was mainly detachment limited. It also supports our second hypothesis. In this study, the slope length was found to have a profound effect on the interior processes for different near-surface hydraulic gradients and rainfall intensities. However, the slope length factor was ignored in interior erosion predictions in former studies. This table presents the comparison of the existing interior erosion equations based on the data from this present study. When the slope length was not considered, the predicted interior erosion rate using model 1 to 3 did not satisfied match the measured value with R² less than 0.5. In addition, model 4 and 5 did not provide improvement by considering the negative exponential of the slope length. In a word, the current models greatly overestimated interior erosion. The results of the present study demonstrate that the dominant processes of interior erosion was transport limited under drainage or saturation conditions, and detachment limited under seepage conditions. Following the method for distinguish detachment and transport limited processes of interior erosion by Wu and Zhang, the interior erodibility should consist of two parts, including interior sediment transportability in transport-limited conditions and interior detachability in detachment-limited conditions. Two equations for transport-limited and detachment-limited was provided. The one-to-one line indicates that the predicted value obtained by our study was very close to the measured values. For the drainage and seepage conditions, the value of R² was 2% to 1,800% higher than the existing equations. The values of RME was decreased by 38% to 87%. It indicates that the provided equations have the potential to predict the slope length affected and also the near-surface hydraulic gradient affected interior erosion processes. 6 REE oxides were applied in different slope segments and soil layers to track sediment movement and deposition in order to gain insight into near-surface hydraulic gradient affect interior erosion processes. And the following 4 main conclusions were obtained. Detailed information, please turn to the publication or feel free to contact me. Thank you for your attention, and welcome to attend the 3rd International Youth Forum of Soil and Water Conservation held by the WASWAC in 2021. Thanks a lot.